My name is Jun Park. I'm originally from South Korea, Busan actually. I'm studying at the University of Minnesota in United States as a PhD student. And sphere, if you think about it, once I fix the dimension, which is an integer, a positive integer, you could have a zero-dimensional sphere, one-dimensional sphere, two-dimensional sphere. But once you fix the dimension, the only thing you probably want to know about a sphere is radius, because once you know the radius, you know its surface area. So it's two-dimensional sphere. You know its surface area, you know its volume, you know its curvature as well. To be honest, this is about all the geometry you could possibly compute on a sphere. And these formulas for surface area, volume, curvature, they're not trivial, But once you compute them, you realize all of these formulas only depend on one thing, which is radius. So what that means is that radius is the invariant of the sphere. So, instead of studying one sphere and another sphere, one at a time, maybe we can see what is a moduli space of a sphere, and that's just a positive real line. You give me some real number, say pi or square root of 3 or 2 or 1, and then I'll have a sphere of that radius, and any kind of geometric information up to isometry is determined uniquely by this geometry. So that's what moduli space is, just the space where the invariants live. The donuts come in because we want to study these four-dimensional spaces. We are a little more ambitious. And four dimension is actually the most important dimension for most mathematicians, because all kinds of interesting phenomena happens in 4 and doesn't happen in 3, it doesn't happen in higher dimension. 4 is, perhaps I could say, we live in a special dimension. But anyway, so instead of studying these spaces as they are, mathematician likes to break space down into simpler pieces. And there's this notion of a fibration, where the fibration structure says, well, maybe I can study this space as a product of surface with a surface. Surface is a two-dimensional, so if you take the product of surface with a surface, you get four-dimension. And oftentimes, what we usually like to study is spaces that are filled with these elliptic curves, where elliptic curve is it looks like a Dunkin' Donut, because elliptic curve, by that definition, means it's a genus one surface.
Something with one hole.
That's right, and probably unless it's most people make donuts with one hole. So, yeah. So elliptic curves are important for many other reasons. Even though it's incredibly important geometry, it has a very important place in number theory, which is queen of mathematics, and also it has found application to cryptography. And it just goes on and on. So apparently you can increase genus, and there are fascinating stories with a higher genus surface. But genus one surface, the elliptic curves and Dunkin' Donuts, have an important place in mathematics, unique place in mathematics, especially also in the four dimensions. So I have to study four-dimensional spaces, and I have to deal with the Dunkin' Donuts. So my work is studying the moduli of semi-stable elliptic surfaces. Basically, I study elliptic surfaces using elliptic curves. So these are higher dimensional Dunkin' Donuts. You can think of it this way, four-dimensional Dunkin' Donuts. And with my recent work, joint with Chang-Ho Han at Harvard, who is a student of Joe Harris, we were able to count how many elliptic surfaces, semi-stable elliptic surfaces, there are over the function fields. But then there is this amazing connection between function fields and number fields called the global fields analogy that says whatever I do in geometry, function field, has analogy to whatever I do in number field, number theory. So I can compute how many elliptic surfaces there are, semi-stable elliptic surfaces there are over the function fields. And this computation, counting that I do, should have analogous asymptotic heuristic on function number fields. And basically, I can now count how many semi-stable elliptic curves there are over the number fields by doing geometry. But this is interesting because the semi-stable elliptic curves over the rationals were exactly the class of curves used by Andrew Wiles, Sir Andrew Wiles now, to prove the first version of the modularity theorem, which was enough to establish Fermat's last theorem as a true theorem. So even though my work isn't, all-encompassing, it has connection to this important piece of mathematics. So I feel very lucky to... I tried many different things, but nothing overwhelmed me as much as mathematics. I like to be overwhelmed, and when you discover a whole new world, because you have to understand certain things, but then when you understand, you realize they all somehow all connect, and then you open an eye to a whole new horizon. and then you feel this feeling of, wow, I'm entering a new world, and I don't know anything about it, but it seems interesting. This kind of overwhelming sense of curiosity and difficulty, abstractness is one of the unique feeling I have in mathematics. Nothing seems that complicated in my life, but to be honest, everything seems complicated, but nothing seems complicated in a way that mathematics does, which is still feel like that young feeling you feel when you're young. You go out to your backyard and everything's new, whereas in mathematics this happens even at old age.